write the examples? No. You guys, this is something that moving forward you can look back on and look at examples and read through your notes. I'm going to start giving half credit again. If you're not writing everything down, I want everything done. I took all this time out of my day so that you guys would have all of this stuff. Ideas that are the takeaway from this unit. The first one is how to define continuity. Our definition of continuity is the limit value is equal to the function value. If the limit value equals the function value at a point, that's how we define continuity, at a specific point. What's cool about that is the flip of it. If I tell you that a function is continuous at a point, then you can tell me that the derivative does exist. Does that make sense? Because it had to have. If the definition of continuity is the limit value, meaning it has a value, and that value is equal to the function value, that's our definition for continuous. If I tell you a function is continuous, then you know for sure that it has a limit value. Does that make sense? Michael, does that make sense?
Yeah.
Okay. So, in order to do that, we need two different definitions for continuous. One on the internal, what's inside. And the other one's for at an endpoint, because you can't take the limit at an endpoint because you can't see to the other side of it. So there's two definitions. That hold the limit value is equal to the function values for the interior and for an endpoint. The function value is equal to a side limit, or a limit from one of the sides. Okay? So if you're coming from this side, that this is continuous from the right, if this limit value equals the limit from the right. And that's how we're going to define continuous at an endpoint, because we can't use that definition at the endpoints. So let's take a look at this function. What is the limit as x approaches 0 for this function? What is the limit as x approaches 0 for this function? It is 0. The limit from the left equals 0. The limit from the right equals 0. Those two limits are the same. So the limit exists and it's equal to that value. What is f of 0? 1. F of 0 is 1. So what does it mean about continuity at 0? There is a discontinuity at x equals 0. What type of discontinuity is? Well, that's when we get into these different definitions. One is removable, one is jump, one is infinite, and one is oscillating. You deal mostly with the first three, but I'm going to show you an example of the fourth one. A removable discontinuity is just at one point. You literally just take the one point off. A jump is a specific length that you jump, that you go from one side to the other. And an infinite is like an asymptote. Those are the three main types of discontinuities. And then the oscillating one, I'll show you an example. So what's the limit as x approaches 1 from the left? From the left is 1. What's the limit as x approaches 1 from the right?
0.
What does that mean about the limit as x approaches 1?
Does not exist.
Does not exist. What's the function value at 1?
0.
It is 0. But as soon as you have that the limit doesn't exist, it's not continuous. You don't have to check anywhere else. Does that make sense? Okay? Alright. So you're going to get removable, jump, and then here's a couple examples of infinite discontinuities. You have the 1 over x function. You know, it goes all the way down. It's a really, really big jump. It's the size of like an infinite jump. It goes all the way up from this side, all the way down. So that's what we call an infinite discontinuity. We also call things like 1 over x squared, even if they go in the same direction, they're both going up from both sides, we still call that an infinite discontinuity. Okay? Everyone on your calculators, graph for me this oscillating thing here. This is the sine of 1 over x. Kind of a fun little function. Make sure you're in radians. And change your window to like -2 to 2 by 1s and -2 to 2 by 1s. -2 to 2 by 1s. Or sine of 1 over x. Make sure you're in radians. Does everyone's graph look like that? What's that? Well, what the heck is happening when x gets really close to 0? Why does it do that? So at 0, this is bad, right? But look, it starts getting really kind of wacky even before that. You know what I'm saying? It starts going wiggle, wiggle, wiggle. It looks like a really squished accordion. Let's take a look at the graph of just the sine of x function. Here's sine of x function, right? It goes 0, and then at pi, it's back to 0, and then at 2 pi, it's back to 0, it goes boom, boom. Here's just a regular sine graph. Well, pi is like 3.14, and this is 6.28. When you start dividing by small numbers, well, what's the difference between 1 over 0.01 and 1 over 0.02? What is this equal to, 0.01? 1 divided by 0.01. What's 1 divided by 0.02?
50.
So this is just a little move on the graph, you know what I'm saying? But the value that we're putting into the sine function has just changed by 50. Well, think about this. Every value of 3, it goes from positive to negative. So even in this little change, you've gone a change of 50, so you've changed sine a whole bunch of times. Does that make sense, you guys? Because we're dividing by this small number, meaning the outputs get really big. They get really big really fast. So as you move on, this thing is going really quick between positive and negative because these are changing so quickly. Does that make sense? That's called an oscillating discontinuity. Okay? So those are the main types. But again, the main thing is if the limit value equals the function value, it is continuous. Now, when I say continuous function, that's completely different than continuous on an interval. And here's some examples of the two. If you talk about a continuous function, well, everything we've been dealing with is a continuous function. Polynomials, lines, quadratics, cubics, rational functions, 1 over x plus 1, absolute value, exponential, log functions, trig functions, radical functions like the square root of x. All of these are all continuous functions. When you say continuous function, Jesus, what we're saying is that function is continuous on its domain. That's what we mean by a continuous function. The definition of that is that function is continuous on its domain. So a good example of a continuous function is our good old pal 1 over x. This, somehow, is defined as a continuous function. Well, what's the domain of this function? Are we including it?
No.
Union?
0 to 3.
Yes,